two fields actually add up together. That's another source of confusion I think I was having. Sorry about that. See, I think even I make mistakes. And that means that the size of this the size of this, 9 e to the 9th times 3 divided by 1.25. Whoops. Let me try that again. 5.5 e to the 9th plus 1.2 e to the 10th. I get a plus 1.8 times 10 to the 10th. Yep, I think that's what I got before. And that's a field heading to the right. The electric field heads to the right. Okay, so now if I put in a negative charge, if I drop a negative charge, remember if I put a positive charge in here, the field's going to the right. I put a positive charge in here, it would want to move to the right. But if I make it a negative charge, like the problem part B says, that's going to make the force, if I have an electric field going this way and a drop in a negative charge, it wants the force is pulled in the opposite direction. And the size is so, it would be this size. It would be 1.8 times 10 to the 10th, 1.8 e 10 to the 10th times 0.00066, and I would get 1.2 times 10 to the 7th newtons, and it's going to the left. So the force is heading to the left, and it's 1.2 times 10 to the 7th newtons. All right. Well, we got through that problem. Now, number 8. No, that was number 8. Now we have number 9. Okay, it's to draw the electric field generated by 3 stationary charges. They are all positive and they are like an equilateral triangle. So we have a positive charge, they're all equal. Positive charge here, positive charge here, and a positive charge here. And the problem is to draw the electric field lines. This is number 9. Well, we have symmetry here, so basically if I'm going to draw 4 field lines coming out of each one. They're all equal size. So basically, if the electric line's coming out, notice there's no negative charge here. So there's no place for the field lines to go other than away from the charges. So what will happen is if I draw a field line coming this way, it will have to bend. Field line coming this way, it will have to bend. The field line coming this way, it will have to bend down. And I need to try to make this as symmetrical as I can. So notice the field lines come out, but they always bend away. I want to try to make that as symmetrical as possible. The field lines all bend away from each other. Okay, and you should look something like that. Now notice the point right in the middle. The point right in the middle, equidistant, what would the electric field be here? The electric field right in the middle would be exactly 0. It would have to be 0 because if we put in here, say, a small plus charge, it's going to feel an equal force this way, and an equal force this way. that are perfectly 120 degrees apart, and the sum of the forces right there will be exactly 0. Therefore, the electric field would have to be 0, because the sum of the forces is right there. So the electric field right at the exact center is 0. Now, just as an example, what would happen, how would this differ if it looked like this? Plus charge here, but a minus charge here. How would you draw this one? It's not in the book. But basically what you'd have, all the lines here, some of the lines would feed into here. So I would have a line here that do this, that would do like this, line here that do this, a line that came this way would be deflected here but come into here. Okay, and you would also have this kind of thing. From here they would still be deflected out, and it would look something like this. Okay. All right, last problem. Okay, number 10. The second orbit of the only electron in the helium ion has a radius. So we have a helium ion which has, remember, is plus 2 protons. And let's say there's only one electron and it's orbiting. And there's a radius here. The radius is 5.29 times 10 to the minus 11 meters. Okay, that's very small. What is the speed of the electron in that orbit? So basically it has a certain velocity, and you want to know what is the velocity. Well, this is according to kind of a very simple kind of circular motion electron model. So basically what we have is we have the Coulomb force, which is equal to K. In the center here we have plus 2 protons, and the electron is 1. So we have plus 2 protons, I'm just going to write it that way, and 1 electron, I'm just going to simply write it that way, divided by r squared. Now that's there's a Coulomb force from here, pulling the electron in to the center. This thing is spinning around, so the force, the Coulomb force, provides the centripetal force. So mathematically that's mass times v squared over r. And the question is, what is the speed? Now the mass of the electron is 9.1 times 10 to the minus 31 kilograms. Okay, so how do we work this? Well, we have the equation, and we just simply, now I'm going to take this basically, and what we have is we have the charge of the proton times the charge of the electron. Okay. Excuse me, the charge of the nucleus. I'm going to write it like this. And really, the charge of the nucleus, the charge of the nucleus is two protons. So it's 2 times 1.6 times 10 to the minus 19 coulombs. And the charge on the electron is 1.6 times 10 to the minus 19 coulombs. Okay, the charge of the electron and the proton are the same, but the nucleus has 2 protons. So notice one of these r's cancel out, and the v squared, I'll put it over here, v squared equals k, q of the nucleus, q of the electron, divided by r, and I divide it also by m, the mass. And then to find the velocity, I simply take the square root. Okay, so I'm just going to plug in these numbers. 9 times 10 to the 9th, and let's also look at the units here. It's very important. We have newtons. Remember, K, this is Newton times meter squared divided by Coulomb squared. We're going to multiply by, basically we have a 2 here, and then we have 1.6 times 10 to the minus 19 coulombs, and we have to square that. So we have one of these times one of these, and we divide by the radius, 5.29 times 10 to the minus 11 meters, divided by the mass, 9.1 times 10 to the minus 31 kilograms, and we take the square root of that. Okay. I'm also going to look at, like I said, I wanted to look at the units here. Okay, so basically we have newtons times meter squared divided by Coulomb squared times Coulomb squared. Up top and below we have meters times kilograms, and we have the square root of all that. Okay, notice that these cancel out, and the Coulomb squared cancels out. One of the meters cancels out with here, and we're left with newtons times meter divided by kilogram square root of. Okay. Well, now what's a newton? A newton, remember, 1 newton of force equals 1 kilogram times meter per second squared. So this will be a kilogram times meter per second squared times meters divided by kilograms times all the square root of. Notice that kilograms cancel out, and we're left with meters squared divided by seconds squared, but we take the square root of that, and we get meters per second, which is a velocity, and that's exactly what we need. So the velocity here is going to come out to be units of meters per second, just like we want it to be. And we get 9 e to the 9th times 2 times 1.6 e to the minus 19, and I square that. Could take a square root immediately, and we divide by 5.29 e to the 19th divided by 9.1 e to the minus 31. These are some awfully big numbers, and we take the square root of all of that. And I think I did something wrong, because I'm getting a number. I think I must have pushed through. Let me try that one more time. Let's also make sure that, let's make sure I did this right. And okay, so 9 e to the 9th times 2 times 1.6 e to the minus 19 divided by 5.29 e to the minus 11 divided by 9.1 e to the minus 31. Okay, and I get the velocity is equal to 3.1 times 10 to the 6 meters per second squared. That's a very, very, very fast velocity. Now, just for fun, let's do something. We have a little bit of time, maybe. Let's try something. That's the velocity. Now remember, we have, here's a radius, and here's a velocity. Okay, let's calculate the frequency, or the period and the frequency. Remember, the radius was, it's not in the book, but 5.29 r equals 5.29 times 10 to the minus 11 meters, 5.2 times 10 to the minus meters, and the velocity was 3.1 times 10 to the 6 meters per second. Let's calculate, just for fun, the how many times per second that actually goes around. How would we do that? Remember, the distance traveled is a velocity times the time. Okay, so the distance traveled is 2 pi r. That's the circumference around, and it's equal to the velocity times the period. Okay, now what I want to do, remember, the frequency is equal to 1 over the period. So really what I want to calculate is the frequency, how many times per second it goes around. So that's equal to the velocity divided by the frequency. So what I'm going to take these two equations, 2 pi r equals the velocity divided by the frequency, or the frequency is the velocity divided by 2 pi r. And we're going to get 3.1 times 10 to the 6. This is all in meters. Meters per second divided by 2 pi times a radius, 5.29 times 10 to the minus 11 meters. Notice I'm going to get a number that's going to be basically cycles per second. That's the same thing as hertz. Okay. 3.1 times e to the 6 divided by 2 divided by pi, whoops, 3.1 e to the 6 divided by 2 divided by pi divided by 5.29 e to the minus 11, and I end up with 9.3 times 10 to the 15th cycles per second, or hertz. Okay. Now, now we haven't talked about this yet. That's a very, very, very high frequency. What is, if that were light, what would be the wavelength of light? Well, we haven't even talked about this yet, but the wavelength times, the wavelength is in meters, wavelength times the frequency is actually the speed of light. Okay, so so the wavelength, if this were light emanating from this at that frequency, it would be the speed of light, which is given the symbol c, divided by the frequency. Okay, so it would be 3 times 10 to the 8th meters per second divided by the frequency of 9.3 times 10 to the 15. That's 1 over seconds, and notice the set 1 over seconds, and we end up with something in meters. 3 e to the 8th divided by 9.3 e to the 15th, and we get 3.2 times 10 to the minus 8th meters. I'm going to put that in nanometers. That's the same thing as times 10 to the, that would be 0.3 or 32 times 10 to the minus 9 meters. The 1 times 10 to the minus 9 meters is nanometers. That's 32 nanometers. That's a very, very, very short wavelength. If this were light, that was a very short wavelength of light in the range of actually much shorter, and then it's almost like a very deep ultraviolet ray, very deep ultraviolet ray. So, well, it just gets you an idea of, well, we haven't even talked about these issues, but we'll talk about this more. In particular, the Bohr radius, the Bohr model of the atom, we'll talk about in the numerical lab dealing with Chapter 13. Well, thank you. We'll talk with you later. Bye. Hello, this is Chapter 13, the lab, an overview of the, in this case, 2 labs for Chapter 13, the electrostatics chapter. Actually, this is one of the few chapters in the second half of the book where we are going to have 2 labs. The first lab is an actual lab that we'll conduct in the in the classroom. The second lab is one of these numerical labs that will require a little bit of explanation and discussion, but it's actually something that you will do actually at home. So we've done this before, having actually 2 labs in one chapter, so I think this is about the last one, if I remember right. That is. Okay, the first one. The first lab that we're going to do is called Electrostatics, Van de Graaff Generators, Coulomb's Law, and Electric Field. And basically, the first couple pages are some information about Van de Graaff generators that I have downloaded from a good science website. And you need to read this. I'm not going to discuss this right now. But it shows on page 3, it shows the inner workings of a Van de Graaff generator and basically how a Van de Graaff generator works. The basics of a Van de Graaff generator. And then on page 3 and 4, and then on page 5, we have a question, a fairly simple question on how to how you might play a trick on a professor on how to deactivate a Van de Graaff generator. Let's see, now that's on page 6. There's question number 1. And on page 7, we have question 2 and question 3. Again, dealing with ionization, that is air being ionized, and basically what we mean by that. And question 3 is dealing with a spark plug. A spark plug is a really great example of where we spark, which ionizes the vapors, in this case of gasoline, is used to produce useful work. Another way that we use, in this case, air gaps, is a lightning arrestor. And then question 4 deals with arcs in a vacuum tube. And then question 5 and 6 deal with particular things that we observe when we deal with the Van de Graaff generator. Van de Graaff generator. And just for the sake of discussion on this, what we're going to do is we're going to show basically a Van de Graaff generator can be thought of we have a motor that's attached to a wheel here, and we have a rubber rubber belt, which continually moves. The rubber belt moves by the action of the motor, and it comes up here, and the rubber belt makes a continual loop. And then what we do is we have a sharp object right here with kind of a metal comb that basically brushes, this metal comb brushes against the metal here, and we purposely put a positive charge on here. Okay. Now what happens, the rubber, rubber is not a conductor, but what it will do, it's not a conductor, but what you can deposit charge onto the rubber, onto the rubber sheet. And the positive charges are actually carried by the rubber up to the top here. And here we have another comb-like structure which basically pulls the positive charges out, and it places them on this metal dome. Okay, and so the positive charges are conducted up or are moved, transported up to here, and then we have a conductor, and this is a metal dome, so the positive charges will equally spread out all over this metal dome. And this will continually build up charge until, well, it will build up charge as long as we keep the motor going. We can continually build up positive charge up onto the metal dome. And this is called a Van de Graaff generator, after the American scientist named Mr. Van de Graaff. And so now, if we get close to this, in this case, what we're going to demonstrate is a small Van de Graaff generator, a tabletop version, one that doesn't build up too much voltage, maybe only 10,000 volts, but very low current. And so if I'm standing over here and I reach out my finger, here's my fingers, and if I'm brave enough, I can get shocked. A big zap, basically a spark will jump from here to my hands because I'm grounded over here. That is, I'm at a much lower potential. My voltage potential is much lower than the voltage potential here, and it actually ionizes the air. In this case, the spark is not a real powerful Van de Graaff generator, so it only produces a spark. Maybe the maximum is about an inch length or so. But it's enough to tingle your hands and things like that. So it's not like this is not a large Van de Graaff generator that could actually electrocute someone and kill them, although there are Van de Graaff generators much larger that are large enough to actually kill a person. Okay, so part of the experiment in page, if you look at page 9, one of the things we do is we set a Barbie doll right here, and someone has provided us a Barbie doll, and the Barbie doll has long hair. Well, we set her on here, and lo and behold, her hair stands up like this. Her hair goes like that, and all the hair just stands right up. Now, what we want you to do is I want you to figure out why does the hair stand up. It has something to do with the plus charges being all on here. Okay? So the plus charges get on here, and of course the plus charges repel each other, and the hair stands up. Now, another thing we're going to do is I turn off the generator, and then I put on here aluminum sheets. And I measure the weight of the aluminum sheets. I turn on the generator. This is the question 6 at the bottom of page 9. I turn on the generator, and then what we observe is one sheet flies off at a time. The top sheet actually flies off. then the second sheet flies off, then the third sheet flies off, and in consecutive order, each of them flies off. So you need to discuss why that happens, and then on page 7, question 7, is we measure the weight, and I want you to approximate the charge that builds up on here. What charge do we have to lift off a sheet, to elevate a sheet? Okay, so this is a very quick lab, very easy lab. Oh, and there's an extra credit problem which deals with this also. Well, this is a very quick lab and kind of a fun lab, but so it's a fairly easy lab to do. And it's all centered around Van de Graaff generators and electric fields and charges. Okay, so this is an easy lab to do, and hopefully easy lab to fill in all the information and answer questions for, because the week after that, I'm going to be handing out a numerical lab, and it's called Physics, Module 13, Hydrogen Spectra Numerical Lab. Now, this is definitely not covered in the book, so I want to, we're going to spend a little bit more time going over this. This information is some fairly detailed information that generally you won't get until you take basically physics in college, and probably more like these